Hi, this is Miss Hammonds. This video is to help you complete your electric circuit notes. I have already typed in the answers to the notes, so hopefully it will make this video shorter than the previous ones I've done. So we're going to start off by looking at our essential question. How are series and parallel circuits similar and different in how they transfer energy? So let's start off by describing what an electrical charge is and what electricity is. So charges of objects depends on whether or not they're giving up or receiving electrons. So objects become positively charged when they lose electrons, and then these objects become negatively charged when they gain electrons. If an object have like charges to positive to negative, they're going to repel. And then objects that have opposite charges will attract. This is what we've discussed in our previous lesson. Electricity is defined as the presence and flow of electrical charges. In this slide, we have a representation of a circuit. You have the little red E's that represent the electrons, and the arrows detect or show you where their flow is. In this series, we have a lamp that will illuminate as these electrical charges flow through it. And then we have a battery that is providing the voltage or energy that's needed to move these electrons. All matter is composed of positive and negative particles. Answer question one, an electric current. Know that an electric current is the flow of charged particles. And I'm going to take this moment and bold that out for you. It's worded a little differently in the slide, but it's the flow of charged particles. All right, so anytime you're home and you're watching TV, using a computer, or even turning the light on into a room, you're needing to have these electrical charges moving into that device. And depending on the device, the amount of electrical energy needed will vary. Looking at question two, higher current equals faster moving electrical charges or faster moving electrons. All right, so in this example, they're giving you a roller coaster. So if you've ever been on a roller coaster, as awesome as they are, some of them are like really exciting and some of them are a rough ride. But the main thing that is similar about roller coasters is that you have a starting point. You'll go through the loops, through the little holes, around trees, however the path takes you. And then when it's all over, you go back to your start point. So you have a fixed path on a roller coaster. Just like roller coasters, electrical currents are on a fixed path. And in the path that they travel depends on the type of circuit that is present. All right, so looking at question four, electric circuits control the movement of the electric current by providing path for electrons to follow. So I'm going to bold this portion out so that's easier for you to see. And then the path of the electric circuit is a closed loop. And we'll look a little bit more in what a closed and open loop looks like and how it affects the movement of the electrical charges. All right, so what's an electric circuit? An electric circuit is what allows electrons to flow from a negative pole, excess electrons, to a positive pole, deficient electrons. All right, so looking at question five, I don't know why it's looking off. I'm going to bold out. That is the flow from a negative pole where you have an excess of electrons to a positive pole where there's a deficient amount of electrons. And so the representation of the positive and negative is the different sides of the battery that we displayed in our previous circuit image. Again, the battery is what provides the energy needed in order to cause these electrons to flow. And so it flows from the negative side, where you have a lot more electrons present, through the circuit. And in some cases, it will illuminate a light along that path, all the way into where there's a positive charge where you don't have as many um, electrons present. And what it's doing is it's feeding those electrons onto the positively charged side. All right. All circuits need to have three basic parts. That is an energy source, which is our battery, wires, and the wires provide the connectivity to all of the objects within our circuit. And then the object that is going to be changed, or should I say charged, in the electrical energy into another form, I guess it is changed, into another form of the energy. That object is what we refer to as the load. So looking at this example, we have our energy source, which is the battery. We have the wires that actually connect a simple circuit. And then the load is what's going to change that electrical energy. So we're taking the energy from those um, electrons in the circuit and we're converting them into light energy. So that's the load. So looking at question 8, and I'm bolding it, it's asking us to explain what is meant by load and then give an example. All right, so before we move on to answering number 8, here are some examples of energy sources. So, and most of what we're going to be looking at, we have batteries, and then in what's used to power our homes, we have a power plant or generator. Excuse me. So that power plant is this large object here that's going through its process to produce energy. And then you have these items that are located throughout our community and then are connected to our homes. So they're like the batteries that provide all of the electrical current inside of our home. All right, looking at question 8, explain what is meant by load and give examples. So changes electrical energy to other forms of energy. That's the load. Some examples are the light bulb, a fan, speakers, a car, and a toaster. And then all of those have been highlighted in our notes as well. And the reason why, let me just add this, the reason why these are considered examples of loads is because they receive some type of electrical energy and then they're changing it to light energy, to mechanical energy, to some type of thermal energy or wind energy. And then the speaker would be some type of sound energy. All right, so sometimes in a circuit, you also contain a switch that is used to open and close the circuit. So if you think about when you walk into a room, that room's wiring is that electrical circuit. And then by the door, typically, or somewhere in the room, you have a switch that you use to power the lights that are in the room. And the reason why you have a switch is because it allows you to open and close the circuit. If power isn't needed to be generated in that room, you will move the switch one way in order to close the circuit. What that means is the connection is broken. Or I'm sorry, to open the circuit. I said the opposite. When it's open, it's not connected. So power sources um, are not being generated, and then objects that need electricity are not on. In a closed circuit, you've connected that circuit. So now power is being moved throughout. So for question 9, what is the purpose of a circuit? I'm sorry, a switch in a circuit. We're going to bold that out. And then it says is that it is used to open and close the circuit. In this next slide, it gives you images of what a open circuit would look like and then what a closed circuit would look like. And so again, in an open circuit, the full amount of electricity is not being used because there's no fixed path for the electricity to travel. In a closed circuit, and if you look at the different lights in each one of these diagrams, this one, the light is not on because the circuit is open. Here, the light is on because the switch has been closed and the circuit is closed. All right, so electrons flow from negative to positive. Therefore, a complete circuit must have wires that connect the negative pole of the energy source to the positive pole of the energy source. The circuit is established when there's a continuous path for electricity to travel from one end of the energy source to the other end of the energy source. So for question 10, where it's asking a complete, or basically is asking you to describe a complete circuit, this second bullet is where I was able to locate the answer. And again, it is established when there's a continuous path for electricity to travel from one end of the energy source to the other end of the energy source. All right, so in this slide, it shows you some illustrations below to show 4 ways in which a simple circuit can be made. And then it just shows you whether or not, um, well, actually, it's just giving you different examples of how the wire, the load, and the energy source are all connected. All right, so for this part of the notes, it doesn't continue on for questions 12 through 15. It actually starts on the next page. So if you could take a moment, scroll to the bottom of the notes where you'll see 2 columns, one that says series and one that says parallel circuit. Again, this information has already been populated for you. So we have 2 types of circuits, circuits that are distinguished based on the way in which loads are connected. These types of circuits is either a series or a parallel. We're going to look at a series circuit first. So in a series circuit, there is only one path for electrical currents or electricity to flow. Everything is connected. There is no opposite direction for it to travel. So again, we said that the energy is going to go from from the negative to the positive side. So this is the negative side of our energy source. We actually have 2 batteries loaded here because more energy is needed because we have 2 light bulbs. So if you look at our arrows, it shows you the direction in which the energy is flowing. For your characteristics, you should note that in a series, and I put D, it should be there. There is only one path for electricity to flow, and that all of the loads in the series share the same circuit. All right. So here, again, we have our 1 battery. We have 3 light bulbs, but there's no different direction in which the energy can flow. Again, they don't have their arrows represented accurately because it should go from the negative side, no, positive side to the negative side. Anyway, this is the side that has the most electrons present, but I think that diagram is represented incorrectly. Okay, so all of the loads in the series share the same current, and if there's a break in the circuit, then all charges will stop. So looking at some advantages and disadvantages. An advantage would be everything that's connected can use that one power source. So if this was a light, this was the TV, this was my computer, all of them are being powered through this one circuit. But the negative is if I were to open my circuit where there's no power to flow, then my lights, my TV, and my computer all just got turned off all at the same time. If there's a break in the circuit will stop flowing. This is beneficial, like if you have a security system or alarm system in your house, and then it's activated. So your doors, your windows, anything that is connected, once it's opened or interfered with, it will trigger that security system to activate and tell you, hey, somebody's coming in, this circuit is broken. All right. So there are some cases when a series circuit is useful. That's where we have our advantages. For example, series circuits are used in wiring burglar alarms. If any part of the circuit in an alarm fails, there will be no current in the system. That lack of current signals that a problem exists, and then the alarm will sound. Kind of like what I just explained to you and just previously. And then here is where there would be a disadvantage. Imagine that your house is wired in a series circuit. What would you have happen, or what would have to happen if you wanted to watch TV? You would have to turn on other appliances in order to watch the TV. It's kind of stupid, right? So circuits in buildings are usually wired in parallels. That's why you're able to turn your TV on, turn the lamps on, all individually instead of everything having to be turned on together. So now we're going to look at the parallel side. And for characteristics, you should copy the information that's located here. In a parallel circuit, there is more than one path for the electric current or electricity to flow. So you still have your one power source, but notice now you have different directions in which the energy flow can go. So we have a bulb here and a bulb there. As far as some advantages and disadvantages, the electric current branches so that electrons flow through each of the paths. If one path is broken, electrons continue to flow through the other path. So think about a situation where you have a lot of light bulbs, and then one of the light bulbs burns out. That one particular light bulb will not um, have a flow of energy because the bulb no longer works. But then in that same area, you have the other bulbs that are still working. You would have a parallel circuit set up in that space or in that room in your home. So that means that the energy that's flowing from this image or from this battery may stop flowing through this particular circuit, but it will continue to flow here and here because they have different paths in which to travel. Only the one that's no longer connected would not work. So again, for the characteristics in a parallel, there is more than one path for the electricity or the electric current to flow. The current branches so that electrons flow through each of the paths. And if one path is broken, electrons continue to flow on the other path. All right, so now that we're done with our series in parallel, we're going to go back to 12. 12 is asking us to describe voltage. And I'm sorry, typically I would try to keep these videos short, but honey, we're trying to do a one and done, and you can fast forward and pause this video as needed to complete your notes. All right, so describe a voltage. In layman terms, voltage is what makes electricity charges move. So looking at this diagram, we have a breaker box, which would be present in your home. And in that box, you have connections to the different circuits located within your home. This is a 10-foot wire that powers this socket in the wall. This socket needs 117 volts. And it's telling you that 3 volts are lost as it travels through this wire. In this part, we have a 100-foot wire, and it's letting us know that 10 volts are lost as it travels through this wire. This particular socket needs 110 volts. So when you look at your cell phone and somewhere on your box, it tells you how many voltage is needed or how many volts are needed to power it up and charge your cell phone. Based on the amount of voltage that's allowed through each one of these sockets, that's how you would kind of determine where you would plug it up. I know some of you guys have that speed charge. Well, the wiring that you have may be able to deliver the voltage to your cell phone faster in order to charge it up faster. All right, moving on. Question 13 is asking that we describe resistance. So I'm going to go ahead and bold that out. So in a series circuit, the current has to travel through each bulb, therefore adding more light bulbs, which makes each bulb dimmer because the resistance of the whole circuit has increased. And resistance is how difficult it is for electrons to flow through material. There's a friction that is caused. When we go back and look at the slide on voltage, remember I described that 3 volts are lost here and 10 volts are lost here. That's based on the friction that is occurring in that wiring, which is causing a reduction in the amount of voltage that's passing through. Question 14, I'm going to go ahead and bold this out for us, describes electrical conductors. And then question 15 is describing electrical insulators. All right, and I'm just going through these slides kind of quickly. Think of the relationship between electrical current, voltage, and resistance shown in the diagram below. So basically you have a woman who has a hose and a bucket of water connected. And so she's holding it at her waist and the water moving out is slow. Then it shows you that she lifts that bucket and the flow of water increases. So as the bucket is raised, potential energy is increased, and we've discussed potential energy in our previous units. So the voltage is increased, and then there's less resistance in the hole, therefore the water flow, also referring to electricity current, is greater. So the lower she has it, there's different directions that the water has to flow. It slows it down a little bit. But when she increases the height or the potential energy, there's an easier flow for the water, whereas there's an easier flow for the electricity. Another advantage of parallel circuits is that you can connect loads that need different currents in the same circuit. I didn't add that one, but you can go back and add it. For example, you can connect a hair dryer, which needs a higher current to run, to the same circuit as the lamp, which needs less current to run. So in this diagram, it says, what does it mean if the light bulb, I'm sorry, it's early. What does it mean if the bulb lights when you touch the wire to the ends of the paper clip? What about one of the other items that's like a piece of chalk or a piece of paper? All right, so now we got into the slides where we'll talk about electrical conductors and electrical insulators. So recall that electrical conductors is a material in which charges can move easily or electrons flow freely. In electrical insulators, this is material in which charges cannot move as easily. Their electrons don't flow freely like they do in electrical conductors. All right, so even though there are some additional slides, those will be discussed live in class. And so this video is now complete, and hopefully you are able to have all of your notes complete. Thank you for taking the time to view this video, and have a great day.